Okay, we are going to talk about systems of DEs, in particular systems of coupled DEs. So in the most general case, you can see here, I've got this entire list of differential equations, and I've got one independent variable, t, and n different dependent variables that I've called x1 through xn. And each of those guys' derivatives, x1 prime, for example, depends on all the other guys. It depends on x1 up through xn. And in front of each of those is some function of t. And then at the end of each of these lines, I have some other function of t that's just like an independent function and isn't multiplied by one of my x's. So I've got this whole system of equations, kind of like a college algebra system of equations that we're trying to solve. But over here, these are all derivatives. And we call this coupled because x1 prime, for example, depends on the other guys, depends on x2 and x3 and so forth. If I just had here x1 prime only depends on x1, and x2 prime only depends on x2 and so forth, we would just solve those independently. Like we would know how to solve each one of those one at a time, and we would have our solution. But that's not what we have. We've got some mixture in all of our formulas. Now, this is the most general form. We're not going to be solving anything that, say, might look like this. So I've got x1 prime is cosine of t times x1, t squared, x2, and then some extra e to the t added on here, and so forth. x2 prime is this function of t times x1, another function of t, x2, and then another function of t. We would have no idea how to solve this guy. We're going to limit ourselves to the case where all of these functions here are constants and where all of these guys over here are zero. So stuff like this. So I've got x1 prime is just 1 times x1 plus 3x2. x2 prime is 5x1 plus 3x2. This guy we'll be able to solve. Okay, so we'll always have constant coefficients in front of our dependent variables, and we're not going to have extra functions hanging out here on the side. At least not these ones that we can solve exactly. Okay, so how do we do this? First, we want to write something like this in matrix form. Now, most of you have not taken a linear algebra or a matrix theory class. So a lot of the stuff we're going to talk about in the next few minutes, you're going to learn a lot more about in a linear algebra class, eigenvalues, eigenvectors, and so forth. But I'm going to teach you everything you need to know to do these. So I want to write my equation in the form some vector x prime equals some matrix A times some vector x. So these guys are vectors, and that guy there is a matrix. Okay, so what do we mean by this vector x? That just means the vector x1 all the way down to xn. It's a vector is in this form is just a column matrix. It's a matrix that is n by 1. This is an n by 1 matrix. Remember, with matrices, it's always rows by columns. I have n rows, 1 column. And then x vector prime is we just take the derivative of each of these guys, x1 prime, x2 prime, all the way down to xn prime. And the matrix A here is made up of all of our little coefficients here. So for example, here, let's rewrite that guy so we have him in front of us. x1 prime was x1 plus 3x2, and x2 prime was 5x1 plus 3x2. So again, we're going to call this vector x, the vector, in this case, x1, x2. Then this guy over here is x prime, vector x prime. So I'm just writing up all the details here so that it will be in this note, these notes. Okay, then we make a matrix out of all of our coefficients here. So our matrix equation will look like this. So there's our matrix A. Here's our vector X and our vector X prime. Now, let's make sure, let's convince ourselves that this makes sense. So what I've written here is this vector x1 prime over x2 prime. Remember, that's not a fraction. I'm not like putting a fraction bar there. 1, 3, 5, 3, x1, x2. Let's convince ourselves that this matrix equation is in fact this system of equations we have here. So how do we multiply matrices? Like you should have learned that in pre-calculus. We're going to take this row and lay it on top of this column. So this is a 2 by 2 multiplying. Remember, it's always rows by columns. Multiplying a 2 by 1. In order to multiply matrices, the insides here have to match, and our answer will be the outsides. So this matrix A times that vector X should give me a 2 by 1. The outsides. The insides have to match. Your answer will be the outsides, a 2 by 1, which is exactly what this guy is. 2 rows, 1 column. He's a 2 by 1. And the top entry in this matrix multiplication should be that guy there. So this should say x1 prime equals, and now I take this row and lay it on top of this column. 1 times x1 plus 3x2. That's what this top element of this matrix multiplication will give me. This row on top of this column. And then the bottom. Take this row, lay it on top of this column, multiply, and add the answers. And that should be this guy over here. x2 prime should be 5x1 plus, it's always a plus in between them, 3x2. But hey, that's exactly what we started with. Okay, so all we're doing right now is rewriting this equation in matrix form. So that's our first step. Our goal is to write x1 or x vector prime is some a times x. Now we're going to assume, here's the theory behind everything that's about to happen. We're going to assume that our solution is some vector, we'll call it k, times e to the lambda t. We're going to assume our solution has this form, a lot like we did when we were doing homogeneous with constant coefficients. Okay, so if we were to take the derivative of that, x1 prime would be lambda times some vector k e to the lambda t. And if I were to plug all that here into this equation, so that's the left-hand side right there. And then here, that's my original, that would go there. Now, e to the lambda t never equals 0. So I could just cancel that out and I would get A times K must be lambda times K. Okay, so just a little bit of matrix theory for you here. In 2D space, for example, this works in all spaces, but just in 2D space for illustration purposes, a matrix rotates a vector. That's what matrices do. When you take some matrix times some vector, all it does is rotate that vector in 2D space. This equation is saying I've got some matrix A and I'm going to multiply it by a vector, and I don't want you to rotate that vector. I want you to give me some multiple of that vector. I want you to still spit out the same vector, but just change its length. That's what this equation is saying. So you've got some matrix. I'm looking for some special vector K and some special number lambda so that when I multiply these guys together, that matrix doesn't rotate my vector. Instead, it just rescales it. We give a special name to a vector and a number that have this property. We call those eigenvectors and eigenvalues. Now, how do we find those? Well, this is clearly true. This equation right here, maybe we'll call this equation star. That's clearly true if the vector k is the zero vector, if it's all zeros. We just get 0 equals 0. That's boring. We call that the trivial solution. We want a non-trivial solution. So what we're going to do is we're going to pull everything over to one side. And again, we're going to get just a little bit of matrix theory here. I want this statement to be true. Now, in the real number system, the only way two things can multiply together to be 0 is if one of those things are 0. That is not true for matrices. It's possible for two matrices to multiply together to be 0 if one of them is not 0, or neither of them are 0. And we're going to use that fact here in a minute. I would like to factor this k out here. I would like to write this a minus lambda, but that doesn't make any sense. This is a matrix. This is a 2 by 2 matrix. Lambda here is just a scalar. It's just a number. You can't take a matrix minus a number. Like, this is meaningless. But what I can do to make this mathematically equivalent to what I have there is put the identity matrix here. So I'm taking lambda times a, in this case, 2 by 2 matrix. Now this makes sense. And I want that to equal, this is a vector over here. I want that to equal the 0 vector. Again, in the real number system, if two things multiply to be 0, one of those things must be 0. That's not true for matrices. It's possible to have two things multiply to be 0 without one of them being 0. Now, we could have k equals 0. We already talked about that. If k is the 0 vector, this is clearly true, but that's boring. That's the trivial solution. So what we want instead is, like I just said, these two matrices, this is a new matrix times this vector, to equal 0 without either of these guys being 0. The only way that's going to happen is if this guy here has 0 for a determinant. So this is only possible, or only non-trivial, I should say, if the determinant of a minus lambda I equals 0. And then we call this number lambda an eigenvalue. and that associated vector K an eigenvector. Eigen is the German word for characteristic. Again, if you take a linear algebra or matrix theory class, you'll see that a matrix A is completely determined by its eigenvalues and eigenvectors. They characterize the matrix. Okay, so we're going to do this here to find our eigenvalues. We find our different lambdas. A 2 by 2 matrix will have two eigenvalues, not necessarily distinct. And each of those eigenvalues will give us a different eigenvector. If our eigenvalues are distinct, then we'll get distinct eigenvectors. And then our general solution will look like our vector x, the thing we're trying to solve for, will be some C1 times some K1. That's a vector, e to the lambda 1t plus C2. These are just constants. C1 and C2 are scalars. They're just constants. Okay, this will make a lot more sense once we do an example. Okay, so let's go back to that example we had. And we'll work it all the way through. Oops. Okay, so we had this example. We've already written it in matrix form. Now I want to find my eigenvalues. So step one, I guess step one was write it in matrix form. But next step, step two, find your eigenvalues, which will generally abbreviate E values. And the way we do that is we want the determinant of the matrix A minus lambda I to be 0. So what do we mean by this? What's A minus lambda I? Well, I here, because we're in 2 by 2 universe, we have 2 rows, 2 columns, will be the identity 2 by 2 identity matrix. It'll be 2 by 2, also just called I2 sometimes. So when I do lambda I, that's just lambda along the main diagonal and 0 everywhere else. So A minus lambda I always just means, this means rewrite A but subtract minus lambda along the main diagonal. So I'm going to rewrite my matrix A, but here along the main diagonal, I'm going to put minus lambda, leave everybody else alone. So A minus lambda I is this new matrix, 1 minus lambda, 3, 5, 3 minus lambda. So leave these two guys alone, put a minus lambda after these elements along the main diagonal. Okay, now we want the determinant of that. So the determinant of 1 minus lambda, 3, 5, 3 minus lambda. And sometimes we'll write that. We write matrices using these square brackets. When we want a determinant, we write like absolute value bars. This is mathematical notation for you're doing a determinant. Okay, do you remember how to do a 2 by 2 determinant? You multiply these minus multiply these. this way minus this way. So that will be 1 minus lambda, 3 minus lambda, minus, now go this way, 3 times 5. Okay, so now let's clean all this up. So we're going to get 3 minus lambda minus 3 lambda, so minus 4 lambda, plus lambda squared, from right there, minus 15. And I want that to equal 0. Let's write that there. Okay, so then we get what we call our characteristic polynomial. Just like we did when we were doing homogeneous DEs. So what do we get here? We get lambda squared minus 4 lambda minus 12 equals 0. Because we got 3 minus 15. All right, that's easy to factor. Lambda plus 2 equals 0, and we get 2 different eigenvalues. We get lambda equals 6 and negative 2. Each one of those separately is going to give us an eigenvector. Eigenvectors go with particular eigenvalues. So step 3, we find our eigenvectors. Okay, so let's look at lambda equals 6. We'll deal with him first. So there are 2 different ways to think about how we calculate eigenvectors. So we could do, I'll write this up both ways. Method 1, we want A times K to equal lambda times K. Method 2, we want A minus lambda I times K to equal 0. Literally the same information. It's the exact same equation. Just here, I've moved everything over to the left-hand side. I think this second one is much easier. But just for completeness, on this first one, I'm going to write it up both ways. And then we're going to use the second way to solve. And then that's what we're going to do from now on. This by far is the easier way. But I just want you to see you could use this. So remember, A was 1, 3, 5, 3. And we've got lambda equals 6. So I've got some vector K that I'm going to call K1, K2. That's what I'm trying to solve for. So I don't know these guys yet. So I want A times vector K to equal lambda, which was 6 right there. That's the guy we're working with right now, times K. Okay, and then I would just multiply across. Remember, this is a 2 by 1, 2 by 2, multiplying with a 2 by 1. So my answer is going to be the outside's 2 by 1. Over here, I have a 2 by 1. The first entry, the top entry here is what I get on top. The second entry is what I get on the bottom. So multiplying here, I would get 1 times K1 plus 3 times K2 equals 6 times K1. Over here on the bottom, 5K1 plus 3K2 equals 6K2. And then I would solve this system of DEs. Or sorry, I would solve this system of equations. Now, this is important to remember. Eigenvectors are not unique. Any multiple of an eigenvector is still an eigenvector. So this system of equations we're trying to solve here is not going to have a unique solution. It has an infinite number of solutions. It's a dependent system. Like you remember back in intermediate algebra, you learned about dependent systems. This is a dependent system, no matter which method we use. Okay, but we could solve this, and any solution works. I'm allowed here to plug in any number I want besides 0 for K1. I could make K1 7, solve for K2. Whatever I get, that solution would satisfy both of these equations, and I've got myself an eigenvector. Method 2, though, I think is much cleaner. So that's A minus lambda I times this vector K should equal the 0 vector. Remember, over here is a vector. All right, so what do we mean here? A minus lambda I. That means take the matrix A and along the main diagonal, subtract lambda. Who was lambda here? It was 6. So that would be 1 minus 6. Leave this guy alone. Leave this guy alone. 3 minus 6. Along the main diagonal, subtract off lambda. So who would that be? That would be 5, 3, 5, 3. This is always going to happen. If you have yourself an eigenvector, this is why the determinant was 0. That's why this happened up here. Remember we said this guy here had to have 0 determinant? What's it mean to have 0 determinant? It means one row is a multiple of the other one. So this is a feature, not a bug. Look what we got here. I got the same row twice. That's always going to happen. This guy here is always going to be a multiple of this one, if you have yourself an eigenvalue that you're subtracting off. That's what we're looking for. Okay, and what do I want? I want that guy times my vector K to equal the 0 vector, which would be 0, 0. Now, you'll notice here, like we're all inconsistent. Sometimes when I'm writing out my vectors, I'll use a square bracket. Sometimes when I'm writing out a vector, I'll just use parenthesis-like notation. It means exactly the same thing. Like if I wanted to be more pedantic, I could write these more square-ish. But we're going to be writing so many of these, it's not necessary. Okay, so now 5 times K1 plus 3K2 should equal the top guy. That's from the top line. And so that's top. From the bottom, I get exactly the same thing. It's not always going to be exactly the same equation, but it's always going to be some multiple of that equation that gives you the same solution. Okay, now I need any solution. I just need any K1 and K2 that work. Any multiple of an eigenvector is still an eigenvector. So I think the easiest way, move this guy to the other side. And I could, when I learned this is the way we would do it. We would always just say, okay, let's let K1 equal 1, and then we would solve for K2. So like, what would we get here? If K1 is 1, I would get 5. So K2 then is what? Negative 5/3. Perfectly fine. I got myself an eigenvector. When I learned this, that's the way we would do it. But I don't want to have to deal with those fractions. So what I think works better is swap coefficients. Swap your coefficients. K1 must be negative 3. K2 must be 5. I switch, because now look, I would get 5 times negative 3 equals negative 3 times 5. So this eigenvector, that went with lambda equals 6 will be the vector -3, 5. Notice I switched the coefficients. I didn't write 5, -3. I wrote -3, 5. Okay, we're halfway done now. That was for my first eigenvalue, lambda equals 6. Now what about the other guy? Lambda equaled, what was he? -2. And I'm going to do this the same way. I want a minus lambda I times my vector k equals some 0 vector. Okay, so a minus lambda I means take regular old a and subtract -2. So that would be, I'm going to write this out in all its glory. 1 minus -2, 3, 5, 3 minus -2. Times some vector here equals some 0 vector. Now, again, I remember when I learned this next step would bother me. I've already used up the symbols K1 and K2. I used them right here. So I didn't like reusing those symbols here. I've already solved for K1 and K2, but that work's already done. I've solved for those guys. I got this eigenvector. I'm allowed to reuse these letters again now if I want to, as long as I keep my work separated. I don't want to have to call this like a K3 and a K4 or a U1 and a U2. I don't want to have to now start introducing new variables. I've already used those guys up, but they're done. I solved for them. I'm moving on with my life. I'm going to use those letters again. I'm going to recycle. Keeping in mind that I'm now looking for a different eigenvector. As long as I keep my work separated, I'll be okay. All right, what do we get here? We get 3, 3, 5, 5. We're almost done. We're getting there. Notice that these rows are not independent. If I take this guy times 5/3, I get this guy. That should always happen. And the two different equations we're going to come up with here are not independent equations. We're really getting the same equation twice. Now, it's always good to check from the top. I get 3k1 plus 3k2 equals the top. And from the bottom, I get 5k1 plus 5k2 equals the bottom. I can use either one of these. I am not solving a system of equations in the sense that I'm getting a unique solution. Use either one of these. If one is prettier than the other, use that one. Because any multiple of an eigenvector is still an eigenvector. So I'm just going to use one. 3k1 plus 3k2 equals 0. So 3k1 is negative 3k2. Like just to have smaller numbers, I'm going to cancel out the 3's. K1 is negative K2. And then this new eigenvector then, I'm going to call it lambda K sub lambda equals -2. Will be some vector, swap the coefficients, -1, 1. Or any multiple of that. I could have had 3, -3. That would work. Or I could have -5, 5. Any multiple of an eigenvector is another eigenvector. Any of those would work, and they'll all give us the same solution. Okay, then, now that we've got all that, my general solution, I'll write this again, has the form C1, my first eigenvector, e to the first eigenvalue t, plus C2, the second eigenvector, e to the second eigenvalue, t. So in this case, and like the C1 and C2, if we swap those, if we switch the order here, that of course that doesn't matter. So C1, what was my K for this eigenvalue? -3, 5. E to the 6t plus C2, the second eigenvector, -1, 1, e to the -2t. Okay, this is a vector equation. Remember, x here, x vector was the vector, and see here now I'm using parentheses instead of the little square brackets. Who cares? Same thing. x1, x2. And that's supposed to equal this. This is it doesn't look like it, but this is a vector. If I go along the top and see now, I'm here just for consistency, I'll use parentheses. If I go along the top here, I get -3c1 e to the 6t minus c2 e to the -2t. Really, it's plus, but I had that -1 there. And then going along the bottom, 5c1 e to the 6t plus 1 times c2 e to the -2t. So in other words, x1 was -3c1 e to the 6t. Here is our actual solution. Plus c2 e to the -2t. So all of that, like we learned a bunch of theory on how to get here, but here's our final solution. This is the solution to this system of differential equations right here. So we find our eigenvalues, find our eigenvectors, and then write the solution. And you could go back and check it. You should. You should go back. Where would I write it first? Right here. You should go back, check and make sure what we just wrote for x1, if I plug it in here and plug in what I wrote for x2, take the derivative of x1, this equation should be true. And similarly here, this equation is now true based on that x1 and x2 we just found. Take the derivative of x2 and so forth. Okay, this is a long video. That's a good place to stop.